I'd be very happy to entertain questions during the talk, particularly if something's unclear and ought to be explained better before I move on. The work I'll be describing is joint with a host of co-authors, many of whom are at Rochester. My student, Mohammed Hedayati, was the principal architect of the Hodor system that I'll be describing. And students Chris Jelkovist and Spiridula Gravani and Ethan Johnson were also involved, as was my colleague, John Criswell. And at Google, at their labs in Madison, Wisconsin, and New York City, Mike Marty and Kai Shen. So for those of you who might be curious and don't know, the University of Rochester is located in Rochester, New York, which is a city of about 1 million people, middle shore of Lake Ontario, the easternmost of the Great Lakes in North America. The nearest really big city to us is Toronto, which is about a 3-hour drive. New York City is in the same state, but it's a good bit farther away, about a 6-hour drive by car. The university sits on a Tennessee River. That's an aerial view of the campus with the river flowing north around the outside of the campus. You can see downtown in the background, and Lake Ontario is at the horizon. I've been at Rochester since 1985. I joined when the department was only about 10 years old. We're a fairly small department with about 20 tenure track faculty, about 70 PhD students, and large undergraduate and master's programs as well. We're probably best known for our work in artificial intelligence and in parallel and distributed systems. To put the work we're talking about today in context, I want to talk just a little bit about operating systems history. So most of us are most familiar with monolithic operating system kernels, where all of the functionality needed to manage resources and enforce policy across applications is in one large address that you enter with a system call. Monolithic kernels tend to be fast, and they are the dominant technology today and have been for decades. But they're hard to understand, they're hard to modify, they're somewhat brittle, they're hard to customize to particular applications, and increasingly in a modern world, security is becoming a problem because anything that compromises anything in the operating system jeopardizes the entire machine. When I was in graduate school, there was a lot of work going on in microkernels. The idea being to increase the modularity of the kernel, to make it easier to make updates, to customize for particular applications, and to contain bugs to individual sort of firewalled components of the operating system. The idea was to export functionality out of the kernel into user-level servers, and then applications would communicate with those servers by sending messages, and the messages would be sent through the kernel. Unfortunately, the message passing through the kernel imposes performance overheads that in practice people have been unwilling to pay for. And for the most part, microkernels are not widely used today, although there certainly are important examples. There's also been a lot of work, both historically and more recently, on so-called library operating systems, which export functionality into user space, but link that functionality directly into user applications. So for instance, an exokernel might allow an application to use particular physical memory pages, but not impose any expectations on how the application was going to manage those pages. And then the library operating system of the application would perform demand paging and virtual memory on top of those physical pages. So in this style of computing, the kernel is involved in setting up access to resources, but subsequently lets applications touch those resources directly, which works fairly well for virtual memory. It doesn't work as well for devices, as we'll see later on in this talk. So at the risk of oversimplifying a bit, we can think of these options graphically as shown on this slide, where the traditional monolithic kernel is over there on the left, and every application interacts with global services and with the hardware only by going through the kernel. In a microkernel shown in the middle, applications get much of their service from user-level server that can then be modularized and more easily updated, but all the communication has to go through the kernel. And in a library operating system, We have direct access from the application into the library, but the library serves the needs of only one application. And each application has its own separate library, and this makes it difficult to enforce global policies. So let's see what we can do to fix that problem of global policy enforcement with library operating systems. We'd really like to go from the library operating system approach on the left to a more sophisticated approach on the right, where each application is able to interact directly with procedure calls into multiple servers, which in turn implement global policy because they're talking to multiple applications. The challenge for this talk is going to be basically how to realize that picture right. It's increasingly important in the modern age, especially in data centers, where our pressures pushing people towards kernel bypass I/O. So let's talk about those performance pressures for a minute. With traditional kernel I/O, applications make system calls in order to read and write files, to perform queries on databases, to send packets over the network, or to receive packets from elsewhere. And the kernel is therefore able to enforce global policies on fairness, quality of service expectations. It's able to recover resources when an application fails, and it bears the responsibility for security to make sure that one application can't damage the resources of another. And all of this is done without the kernel needing to trust the applications at all. But all of the communication goes through the kernel and suffers the overhead of, first, the context switching, and second, the need for a general purpose code path through the kernel. So you can't really customize the kernel to the expected usage pattern of an individual application the way you could with a library operating system. So to eliminate these overheads and to implement optimizations that are tuned to particular applications, many data center providers, the Googles and Facebooks of the world, are now doing kernel bypass I/O, where applications make calls into the operating system to set up access to a device, but the device then talks directly to those applications afterwards. This is sometimes called separating the control plane and the data plane of the application. The operating system is on the control plane that does setup. It's not in the loop on the data plane, which does the routine operations on the hardware resource. So if, for instance, we have two applications sending packets over a network, we need to use a network interface card that can do I/O virtualization, and it provides separate I/O registers to each of the two applications. Those registers are set up by the kernel, and then the applications can touch the device registers directly. But the only fairness that we get, the only division of resources and scheduling that we get, is whatever the device itself does in hardware in its I/O virtualization mechanism. And that's probably just round-robin scheduling across the request queues of the applications. So if application 1 is sending larger packets over the network than application 2 is, it's likely that application 1 will get more network bandwidth. Or if application 1 creates multiple connections to the device, it can basically steal extra bandwidth that is taken away from other applications. And because the operating system is not involved on the data path, on the routine operations on the device, it has no way of getting back into control and enforcing the global policy that is, after all, supposed to be the operating system's responsibility. So in this talk, I would like to describe a system we've been building that we call Hodor. The name comes from the Game of Thrones TV show, if you're familiar with that, that's designed to provide library operating systems with the ability to talk to multiple applications so that they can enforce global policy. And I'll describe first the main architecture of Hodor, then how we implement the memory protection that's needed in order to enforce policy in the library without applications being able to undermine it. I'll present some performance results, and then I'll talk more about sharing across applications before concluding. So the idea in Hodor is the idea of a protected library. And here's a picture illustrating a single application using two different protected libraries. Those libraries may be providing different services, as storage on the left in this picture and network access on the right in the picture. The application makes subroutine calls into the libraries and executes code of the libraries using its own threads. So no context switch is required in order to execute network code or storage code in this picture. The idea is also that when executing the library code, we should be able to access the resources. But when we're executing code in the main application, we should not be able to access the resources, and that should be enforced. This way, if we trust the library code because it's been developed by super users, and we then link that library code into the application in some special way, we'll make sure that the application can only touch the device when it's doing it following accepted protocols as implemented by the libraries. And that change in ability to access resources is enforced by these trampolines. Those are library calls that change permissions, library interface code that changes permissions as we go into the library code. We need to figure out how we're going to implement that. More on that in a minute. So for the user, one develops a library and makes it available to the system, tests it, some super user installs it, makes it available to applications. Then a special trusted loader is responsible for taking the libraries and the applications and linking them together and inserting the appropriate trampolines to create the application picture that we had in the previous slide. Some help is needed from a slightly modified kernel in order to ensure the integrity of the library interface detection mechanism that was provided by the loader. So the loader and the kernel that has been modified together constitute the bulk of. So how do we implement this isolation? Back in this slide, how do we make sure that we can't access the protected resource when we're executing code up in the main application? And there's multiple possible ways we could do this. One is to have separate address spaces and to switch address spaces when we make a call into the library. That can be done with conventional hardware, but it has a high switching overhead. We could instead rely on a trusted compiler to do software fault isolation. This is a technique that's widely used in the security community today. It's sometimes called sandboxing. The compiler basically instruments all the code that might try to touch a protected resource and will deliberately crash the application if it tries to touch a resource that it isn't currently allowed to. The problem with sandboxing is that every access to memory inside the application has to be instrumented to put a check on it. And the check induces overhead on routine execution in the application, even when it's not doing anything with a protected resource. A third option, as used in some library operating systems, notably the Dune system, is virtualization, using the hardware virtualization mechanisms built into modern x86 and other machines. So the hardware then enforces the separation, provides a single protection domain, but the switching overhead is still fairly high. One does a VM exit in order to get into the trusted code. And anytime the application that is using virtualization for our protected library, and it tries to do a global service, whether it's in the library or in the main kernel, it has to hardware virtualization, which is a fairly expensive operation. Moreover, the hardware virtualization implements two-level paging, double the cost on a page fault because you have to traverse more page tables, and that imposes a cost on the ordinary execution of the application, even when it's not accessing the protected resources. Yet another option on recent Intel machines is an enhancement to virtualization called VM-Func, which allows a system on the control plane to set up ahead of time a pre-approved set of second level pages. Those are the pages within the virtual machine that are used for things like the operating system and the application of the guest being separate. If you pre-approve multiple page tables at the second level, the VM-func instruction can be used to switch between tables at very low overhead. This is only available within virtualization, however. And finally, again on recent Intel machines, there's a mechanism called user space protection keys. PKU is Intel's abbreviation. It stands for Protections for User Space. It's an idea that comes from a long tradition at IBM all the way back to the IBM 370 that basically allows an application to reduce its access rights when it wants. And this is the mechanism that we've ended up using primarily in Hodor. It's also been used in a concurrently developed system called ARM at the Max Planck Institute, and that's the other paper that I've mentioned in the citation on the slide. So just to compare these possible strategies, ignoring software fault isolation for the moment, we can think about the cost of an empty call in a protected library. For comparison purposes on the left, I've shown the roughly 9 cycles it takes to switch stacks without imposing any protection at all. So that's the perfect maximum performance case, 9 cycles to get into a library and back if we weren't paying for protection at all. If we switch page tables, we're up to well over 500 cycles in order to change the page table root pointer in a modern Linux system. And if we're doing page table isolation, as we might if we're trying to mitigate the meltdown attacks on recent x86 processors, that cost goes up to almost 1,000 cycles. By comparison, if we're running inside a virtual machine, we can use VM-func to switch between protection domains in less than 300 cycles, but the protection keys for user space get us down to just barely 100 cycles, or less than 100 cycles of marginal cost for protection on top of what it would normally take to do the library call. So let's talk a little bit more about how PKU works. Many people aren't aware that this is available in all server class Intel x86 processors since Skylake. It's a general mechanism called memory protection keys that Intel calls protection keys for user space. So 2 different 3-letter acronyms there. It leverages 4 previously unused bits in a page table entry. So the page table entry up near the top has in bits 59 through 62 a 4-bit field that was not previously used and is now called the protection key. That means that each page can be associated with one of 16, or 2 to the 4th, different protection domains. And then there's a new register available called the PKRU, Protection Key Register for User Space, that's 32 bits long, providing 2 bits for each of the possible values of the protection key. So for each possible key value, there's a pair of bits in the PKRU that tells you whether write access or read access or both should be eliminated for this page for data accesses. Importantly, the PKRU has no effect on instruction accesses. It's only for data accesses in the instruction set, and it cannot be used to increase permissions, only to decrease permissions. So an application that's given the right to do certain things can voluntarily relinquish that right by setting bits in the PKRU. This feature was introduced in the hardware for safety but not protection. That is, as a way to catch bugs, but not to prevent malicious behavior. So an application that has some sensitive information could use the PKU to make it unlikely that that information would accidentally be damaged by code elsewhere in the application. But we can actually use this for security if we want, if we're careful about enforcing its use. So going back to our Hodor picture, we have a main application and 2 libraries here, and we can choose to associate protection keys with them so that when the main application is running, its data accesses to its own data have protection key have the protection key that I've drawn in purple here, meaning that code that's running in this application, while it's running, will choose to set up the PKRU so that only purple data can be accessed. But when it makes a subroutine call into this library, it will execute an instruction to change the PKRU and to make both purple and pink data accessible. So now the library code can access the data structures of the library and can also access the data structures of the main application. Similarly, when the application calls into the green library on the right for network access, the trampoline call will change the PKRU to make both the purple and the green data visible and writable to the library. Unfortunately, as described so far, this design is not safe. We have to worry about the possibility that an application may change the PKRU somewhere other than in the trampoline. So yes, the trampoline call makes the library accessible when you transition in, and it makes the library inaccessible when you transition out. But a malicious application or even just a buggy application could change the PKRU and make the library data accessible to the main application unless we do something about it. And Hodor does. So the PKRU register is written by an instruction whose acronym has the very long name WRPKRU, and it has the binary representation 0F01EF. So the Hodor loader, which brings an application into memory to run, scans that application's binary for any occurrence of the 3-byte sequence that's capable of changing the PKRU. That can happen because there is a real WRPKRU instruction, as shown in the left in this figure. That instruction could be one that's in a trampoline, in which case the library or the Hodor loader will allow it to remain, or it could be in the main application, in which case it's a cause for concern. It's also possible that that 3-byte sequence could be an accident. So for instance, the LEA instruction followed by an add instruction with appropriate arguments can produce a misaligned 3-byte sequence that looks like a WRPKRU instruction. And unfortunately, it is undecidable to decode x86 instructions. So we can't tell at load time whether something is actually an instruction as shown on the left, or is a misaligned sequence of bytes as shown on the right, or is perhaps an embedded floating point constant in a load immediate instruction that just happens to have that 3-byte sequence as well. So the Hodor loader scans the application and looks for all possible occurrences of that 3-byte sequence and uses the debug registers to put a breakpoint each such sequence that it finds. That way, if we actually execute a WRPKRU instruction that's not in a trampoline, it will have a breakpoint on it, and we'll trap into the operating system, and the modified OS can look at the application and say, oh, you just executed this instruction outside of a trampoline. That's not allowed, and we'll terminate the application. On the other hand, if it's misaligned, we will never hit it, because execution will never drop onto a misaligned sequence, and so the breakpoint will have no performance impact whatsoever. Unfortunately, there are only 4 breakpoint registers. And if we run out of breakpoint registers for a particular application, we have to start multiplexing them. That is possible. Fortunately, it's almost required, as I'll show on a subsequent slide. Just to tell you how it's possible, if we discover that we need to breakpoint more than 4 instances of a WRPKRU instruction, then we take some of the pages containing those instructions and we mark them as non-executable. And then if we try to execute one of those pages in the page fault handler, we make the page executable, and we take some other page that has breakpoints on it and we make it non-executable and move the breakpoints over to the new page. Obviously, we don't want to do that very much. So the question arises, how often is this a problem? Remember, of course, that unaligned, implicit instances of the instruction sequence and embedded data never incur any runtime cost. Explicit instances, because some applications really do use WRPKRU for their own purposes. And if they use it to do something that is unrelated to protected libraries, that's perfectly okay, and we can support it. They will be using the library routine designed for this purpose called pkset, which already exists in Linux. And the Hodor library loader understands the pkset library routine and doesn't put a breakpoint there. For other instances that might be an indication of a bug or malice in the application, we do have to be concerned. So to get a sense of how often this is likely to happen, we downloaded all 58,000 plus binary packages available for Fedora 29. That's 108,000 separate executables, and we scanned them all. There were only 123 binaries that had one or more instances of the WRPKUR instruction in them. And only 2 of those 58,000 libraries had more than 4 instances. So we figure the cost of this, the need for the page fault mechanism is very, very close to zero, particularly given that if you knew you had Hodor on your system, you would modify your compiler never to issue the misaligned LEA add combination that produces an apparent WRPKRU. It's easy to change the compiler so that it just never produces that sequence, and that would almost certainly get rid of the need for any use of the page fault workaround. For performance comparisons, we have evaluated Hodor and compared its performance to that of other possible implementations of a protected library, one of which uses separate page tables and does a quick kernel call to switch page tables, another of which uses the VM func mechanism to switch between page tables in the upper level of hardware virtualization. We then evaluated these 3 alternatives on top of several applications. On the left in this picture, Redis is an in-memory key value store, which is quite widely used and is designed to serve requests that come into it over the network over a TCP/IP stack. We modified Redis to use kernel-bypass I/O instead of the normal kernel interface for TCP/IP, and then we linked Redis with the fstack TCP implementation on top of Intel's DPDK packet processing library, and then ran it on an InfiniBand network with a network interface card from Mellanox that can do I/O virtualization. On the right, we took the Silo database, which is an in-memory database designed to be linked as a library into a multi-threaded application. Silo is not meant for sharing across applications. It's designed for use inside a single high-performance multi-threaded application, and it's used in a variety of commercial systems these days. We use and an in-memory key value store and an in-memory online transaction processing interface. And then on top of it, we ran the YCSB and TPC-C benchmarks to evaluate the cost of using this in-memory database as a protected library. In this slide, we can see some of the resulting performance experiment data. On the left, we have the Redis experiment. Each bar measures through, in this case, in hundreds of thousands of transactions per second. The red bar represents the default unprotected case. So for the case of Redis, direct access to the stack and DPDK libraries, but without any protection to prevent the application from damaging those libraries if it were malicious or made a mistake. So that's the best performance we can possibly expect. The yellow bar is Hodor. And you can see that it's getting within about 98% of the throughput of the Linux case. VM Func in this case is approximately equal in performance. It depends some on the size of the packets that are being transmitted, but both of those implementations work pretty well for this particular application. Page table switching is a little bit lower performance. That's the sort of royal blue second bar. Page table switching with page table isolation for meltdown mitigation is substantially slower, because going into the kernel to switch page tables is more expensive in a system that does page table isolation. With Silo, the differences are even more pronounced, where we're doing shared memory access rather than network I/O. On YCSB, Silo reaches more than 2 million transactions per second per core, well over that in the unprotected case, which is really a very high I/O rate. If you think about it, over 2 million transactions per second per core. Hodor comes within 90% of that on YCSB and within 98% of it on TPCC. And again, the other alternatives are somewhat slower, particularly on Silo with YCSB. The page table switching and VM function options are noticeably slower than we get with Hodor. And it's a trade-off that any particular user is going to have to make, but our feeling is that less than 10% overhead compared to the unprotected case in order to get full safety for your kernel bypass library is a pretty good deal. So the last thing that I want to talk about, and I'm actually making better time in the talk than I had expected, so we'll have plenty of time for questions, and I can take as much time as needed on this particular part. Hodor provides a mechanism not only for fast access to a library operating system without making that library OS vulnerable to errors in the application, it also provides the opportunity to share the library between applications. So in this very schematic picture that I put on the slide here at right, we have two applications, each of which has been linked to an instance of some protected library. It might be the I/O stack for FStack and DPDK for network access. It might be the Silo database. Both applications are linked with a library to access that resource, and the resource is in the intersection. It's accessible to both library instances, and we can actually know, if we trust the library code, that application 1 will not be able to damage application 2's access to the library. And in the case of network I/O, we can use the intersection to hold information that describes quality of service guarantees, so that the library code in each instance understands what share of the network bandwidth it has been given and will take only that amount of bandwidth, exactly the same way that the library code in a monolithic kernel already understands the share of the bandwidth that is available to the application that it currently represents and will not take more than that share of the bandwidth. So, as an example of this sharing, we've taken the very widely used Memcached key value store and have re-implemented it as a Hodor protected library, making it available to multiple applications concurrently. Before describing the Memcached experiment in detail, I point out one of the characteristics of sharing in a case like Memcached that I find particularly intriguing as a researcher in concurrent data structures. Many of you in the audience will be familiar with the concept of non-blocking data structures, which are concurrent data structures designed in such a way that there is no reachable state of the system in which a thread will be unable to make forward progress without help from its peers. That's, of course, not true in any lock-based application. If a peer holds a lock, my thread can't make forward progress until that peer lets go of the lock. But in a non-blocking application, I can proceed regardless of what my peers are doing at any time. Such applications are very tricky to write, but They can often have very good performance, and they're not vulnerable to performance anomalies caused by preemption. So they've become increasingly popular in operating systems and language runtime systems and libraries in recent years. The theory community, which was responsible for developing these structures back in the 1990s, was largely motivated by fault-tolerant goals. The idea being, I want a data structure to be shared by multiple threads, and if one thread dies, it will not prevent the other threads from continuing to use the data structure. And this was how theoreticians thought about non-blocking data structures for years. But systems people looked at it and said, well, we don't do that anyway. Threads that share data are part of a single protection domain. Nobody creates a concurrent data structure and shared by threads that don't trust each other. They're all part of one application. If the application crashes, then all the threads are gone. So individual threads dying has just never been historically a compelling motivation for the systems community. Instead, all the uptake of non-blocking concurrent data structures has been because of concern about priority inversion and preemption. I don't want my thread not to be able to make progress because your thread's been preempted by the operating system. Or I don't want my signal handler to be able to make progress because the main application was preempted by a signal and it holds a lock. With a non-blocking data structure, those concerns go away. The cool thing about shared protected libraries is that that original motivation of tolerating individual process failures comes back. And the whole reason that we develop non-blocking structures in the theory community finds new life, I think, in the systems world if we move to the use of shared protected libraries. So get off my soapbox for a second. Let's go back to Memcached. Memcached is a key value store that is widely used in academia and industry. It's used in a lot of data centers with large numbers of machines. It's also used in smaller operations, a lot of small e-commerce sites that run on individual shared memory multiprocessors use Memcached to hold information about their backend database or file system. Typically, processes access Memcached over the network. So in a data center, you'd have a server that's running Memcached, and other machines would send requests over the network for information in the key value store. But it's also used within a single machine with client processes running on the same multi-core hardware that's running Memcached and using Unix domain sockets through the operating system to access the Memcached server. But if you're running on a single shared memory machine, that particular use case of Memcached, the overhead of communicating over Unix domain sockets through the kernel really seems unfortunate. It's like the overhead of communicating with a server in a microkernel system. Why not access the resource directly? And that's what we decided to do with Memcached on top of Hodor. So we took the original code, the most recent release downloaded from the open source repository, and inside we made multiple changes. First, we replaced the memory allocator, which was a custom slab-based allocator designed for Memcached. We replaced it with the non-blocking memory allocator named Rallic that had recently been developed in our group. If you're curious to know more about Rallic, it's a paper by Wentao Tsai and others at the International Symposium on Memory Management just this past month. With Rallic, we got convenient access to shared data and an easy upgrade path in the future to non-volatile memory, although we did not use that yet. We also elided all the network code, and there's a lot of network code inside of Memcached, particularly devoted to batching requests in order to amortize the cost of packet communication over a larger number of lookups or inserts or removes. We took all that code out. Then we added the trampolines and the shared memory labels that have to be added in order for the Hodor loader to bring your program in and set it up correctly. And we rely on Hodor to complete the execution of a library call that's in progress when a process crashes. That requires a little bit more explanation. Memcached uses locks internally. It's not a non-blocking application. So it would be bad if an application called into our protected library, acquired a lock, and started working on Memcached, and then some other thread in the application over which Hodor has no control segfaults. And the process crashes, including the thread that's executing the library code and holding a lock, because then the process would die while holding a lock, and other processes wouldn't be able to access those buckets of the hash table. Because of this possibility, Hodor is designed to ensure that any thread that is executing in a protected library is permitted to finish its library call before the operating system cleans up the crashing process. Now, the OS has limited patience, of course. It won't let a library call execute forever. There's a bound on how long it can be, and that bound is provided to programmers who are advised to make sure that their library calls always take lots less than that bound so that there's never any danger of running out. Now, when a process crashes, presumably because of a bug outside the library, because we trust the library, the process may need to be terminated, it may need to be cleaned up by the operating system, but in the process of cleaning it up, the OS will allow the thread that's in the library to finish its library call and release all of its locks. And we rely on that in Memcached. So here's some performance results. We started with about 26,000 lines of code. That's the size of Memcached if you download it from the repository. To that, we needed to add about 600 lines of code in order to build the trampolines for Hodor. At the same time, we removed almost 7,000 lines of code, mostly devoted to the network, also to some degree to the slab allocator that we replaced with Relic. In fairness, that 600 lines of code does not include the implementation of Relic, but Relic is a general purpose package used by multiple applications, and so it seems at least somewhat fair not to count it in the added code. So in terms of the complexity of the application, it's at least plausible to argue that Memcached for a single shared memory machine without network capabilities is a significantly simpler creature when built with Hodor than it is in the original Unix domain socket version. Individual operations get dramatically faster. So one lookup in the hash table is about 56 times faster than it is if communicating with the Memcached server over Unix domain sockets on the same multi-core machine. Throughput is a little bit more complicated because in the default Memcached case, you can have lots of network packets in flight. So the latency and the bandwidth behave rather differently. A single client in the original Memcached gets very low bandwidth if it has to do synchronous requests and wait for a response to the first request before making a second request. But with a large number of clients, you can get a lot of throughput by having lots of network requests in flight. A more detailed understanding of throughput can be seen in the graph that you've all been wondering about since I've been talking about other things while I had it up on the slide. There are 4 curves in this graph. The 2 upper curves are for Hodor, and the one with the pink boxes is the one that you really care about. That has real protection. The blue stars are Hodor with the protection key mechanism turned off. So you can see what the marginal cost of protecting the library is. And clearly, it's not much. We get most of the bandwidth in the curve with the pink boxes, and we get only slightly more bandwidth if we take the protection out and move up to the blue stars. The other 2 curves are traditional Memcached configured with different numbers of server threads. So the green line has 4 server threads, and each point shows the bandwidth that we get with those 4 server threads and the number of client threads shown on the x-axis. This distinction between server and client threads, of course, doesn't apply in the Hodor case because in Hodor, each thread is performing its own operations on the key value store. We get better bandwidth with 8 threads in the Memcached server, even though we have gone beyond the 20 hardware contexts available on the machine. So this is a 10-core, 20 hyperthread machine that we're running on. You might wonder why we continue to get better performance on the red curve even after we've used up all the contexts on the machine, and that's simply because there are more requests in flight through the Unix domain socket system with a larger number of clients. So bottom line, we are getting at least twice the bandwidth out of the Hodor version of Memcached and up to 50 times improvement in latency compared to the original version. And this seems like a pretty good deal. There are some caveats. Protected libraries have to be written with care. And that shouldn't be a surprise because kernel code has to be written with care. And we're basically using the protected library to implement stuff that we would have implemented in the kernel before. So you can't fail inside library code. It has to be bug-free. If the Hodor kernel discovers a bug in the library code, like divide by 0 or something, then it will just blow away every application that's using that library on the assumption that the library code is no longer trustworthy. So write the code carefully, debug it very well, don't deploy it until you really trust it. All operations, as I mentioned before, have to complete in bounded time. The kernel has limited patience. When it's cleaning up a process or when it's doing a context switch between processes, it will allow a library routine to finish if it finishes within a reasonable amount of time. Third, code in the trusted library can't trust code that came from the user, just as every kernel call starts by validating its arguments and making sure that all expected preconditions hold for those arguments. So too must code in a Hodor library validate the arguments that it was given by the application. And it can't count on those arguments staying intact if they reside in the main application's data space. So if the application makes a call into Hodor, provides arguments that pass validation, but some other thread in the application then, right after the validation, goes and modifies the arguments in place before the Hodor library uses them, problems could ensue. So again, the analogy to the kernel holds. Kernels do copy from user space before they start manipulating data that is critical for correct behavior in the kernel. They won't do repeated reads from user space without revalidating. And so too must a Hodor library not count on user data not to change. And if that data needs to be valid in order to avoid crashes inside the library, then you need to copy it out of user space into the library space before doing the validation. And similarly, when copying back, you can't count on the memory space being intact. So there's this worry that while you're copying results back from the library into the application, some other thread of the application might do a PKRU change, or might even do a kernel call that changes page mappings, and suddenly the library would segfault. There's no way to prevent that, but the library can always do it as the very last thing. After performing its operation, after dropping all locks so that no other instance of the library is dependent on the correct behavior of this library instance anymore, then we can copy back to user space. And if the user does something bad while we're copying back to user space, we don't care. The user program will die, but other instances of the library will be fine. And again, these are the same rules that always apply when writing kernel code. And they're the reason why I wouldn't automatically say that the Hodor version of Memcached is simpler than the original version. It's smaller, but it had to be written carefully with these caveats in mind. So to conclude here, I've introduced the notion of protected libraries and shown that the protection keys for user space mechanism on recent Intel hardware can be used to implement protected libraries safely and with very high performance, giving us, for several important applications, 90+% of the throughput that we could get without protection. I've also shown that libraries can be used to enforce global operating system policy, things like quality of service for network access across applications, even though those applications are doing direct kernel bypass I/O. This allows mutually untrusting applications to share a protected library safely and to execute the server code, the code that would have been in another process in a microkernel or would have been inside the monolithic kernel of a traditional system, to execute that code with their own threads without doing any interprocess communication. And we used Memcached as an example of that. This opens up, I think, a really appealing area for future OS research, where we could choose to incrementally move functionality out of the kernel into user space, where it becomes easier to customize it, to optimize performance for particular applications, easier to implement and deploy bug fixes that don't require everybody to reboot a new kernel on their machine, and easier to contain bugs to improve the security of the systems we all depend on going forward. And with that, I would be more than happy to take questions. Thank you all for tuning in.
Thank you, Michael. It was a pleasure and it was a great talk. And the very first question comes from Alexei. And the question is, well, how many Hodor messages per second can the system sustain?
The number depends a little bit, on your hardware and on what, if anything, you're doing inside the library, but several million per second per core.
Yeah, that was kind of a twist, because you mentioned the source of the naming, and there should be probably lots of Hodor words coming in, and it is kind of funny you don't really use it for benchmarking. Anyway, let's proceed to the questions.
And I'm not sure I understand.
The first question for... Oh, okay, I see. I mean, somebody should pronounce things like Hodor, and the library should kind of protect or do something with it. So that was the question. Okay, Andre wonders, why do you use debugging registers to identify like WRPKRU instruction? Or why don't you replace the instruction at the load time?
We don't know whether it's really an instruction. So there's a 3-byte sequence, and we don't know whether the first byte is at an instruction boundary or not. And it's actually undecidable. If we had a trusted compiler, this would be easier. But if we want to allow the user to run kind of arbitrary code that came out of any compiler, then we can't tell for sure on the x86, because it's a gosh awful instruction set. We can't tell where the instruction boundaries are. And basically, we're trying to make sure that that we've caught the places that are using WRPKU are that are writing the PKRU that shouldn't be, but messing up anything else. So if we replaced that 3 instruction sequence, or that 3 bytes, with no ops, and it turned out it was the end of an LEA and the beginning of an add, then we'd be in trouble. We'd have broken the application.
Yeah, and when you speak of a custom compiler, that should include their user-provided literals. Like if someone is having like int or long literal with some sensitive sequence of bytes, the compiler should transform it somehow into, I don't know, fake addition or some kind of operation.
Yeah, it may or may not be possible to eliminate every possible instance of it, but an awful lot of them you can get rid of. Notice in particular that constants in the data space are not an issue. The only issue is constants that are in code space. And those are typically immediate constants that are being used to load a register. And if you're loading a constant into a register, you can choose to load the upper half and or in the lower half with a different instruction sequence if you want.
Yeah, and can you please clarify how do you deal with dynamically generated code?
If you generate new code at runtime, in order to make it executable, you have to do a kernel call. And when you do a kernel call, the kernel will vet it exactly the same way that the Hodor loader vets the original statically loaded program. And that's implemented. If you do an mprotect call to take some section of your address space and make it executable, the kernel will go over it to make sure that you aren't using the PKRU inappropriately.
Okay, okay, cool. And well, do you have early adopters for the technology, or is it
Just
research
our
only for
group.
now?
Just our group. This was a big chunk of the thesis work of Mohammed Hedayati, who is my senior student. He has recently accepted a position at Google in Seattle, in Washington State, in the US, and defending his thesis next month. I have another student, Beetle, who is planning to use Hodor to do operating system modularization. That's his thesis topic. And right now he is in the process of taking over the maintenance of Hodor. And it's a little bit of a rough process, right? Anytime you have student written code, it's being taken over by somebody else. There's some effort involved in getting it to the point where a new person can pick it up. And the nice thing about doing this is that then producing a version that we can open source for use elsewhere will be easier than it would have been if there'd only been one student involved originally.
Okay, okay. And there is a question regarding zero copy possibility. You said that we cannot really trust the data to be intact, and we have to copy it before processing. And the question is, can we probably use the same debugging registers or kind of trap, like hardware traps, to figure out if the data is modified?
That's a good question. I think figuring out how to do zero copy IO in a Hodor system safely is an interesting topic to explore. I think it should be doable, and clever use of the debug registers is one possibility. Pinning data and preventing it from being remapped will help with the copying out into a void space problem. In some applications, we may not care. So if I'm doing zero copy IO and I'm just writing out a buffer, and all you gave me was a buffer, I'm not looking at the contents of the buffer in order to decide what to do. So my correctness doesn't depend on the data. All I'm doing is shipping the data to the wire. If you modify it while I'm shipping it, you lose. But that doesn't do me any harm.
Okay, okay, I see. And it looks like the integration of Hodor kind of system to the application includes some buffering or queuing at the application side. Is it right that the pattern is like you introduce queue at the sender and receiver side, and then Hodor does the data transfer from one to another?
You could do that, but more often, we hope you'll let the application thread do the real work. So in Memcached, for instance, we do not, in our version of Memcached, we do not have server threads anymore. Instead of the application putting something into a shared memory queue that the server thread pulls stuff out of, which we could have done, we instead have the application thread do the lookup or do the insert or do the remove on the key value store directly in its own context. And the advantage of that is that we avoid the context switching overhead.
Okay, and that basically makes Memcached not as a server, but it is used as a library. So application
Yeah, it's a
code
protected
compiles.
library. But
Okay, okay.
yeah,
So,
but
so
the thing that's really unusual It's a library that's linked into multiple mutually untrusting applications simultaneously.
Yeah, okay. And their idea is it enables, I mean, Hodor enables to trustfully communicate between their applications, right? So they can share their shared segment, shared memory.
Right. Yep. As in this picture.
Okay. And there.
So the key value store is in the intersection of those two yellow ellipses in this picture.
Oh, great. Thanks you for bringing this up. And there is an extra question, like the limitation for this register was something between 16 or so protection zones, right? Does it
Right.
mean
We get
we
only
can have a
16 protection units.
can you please clarify how does it limit the application?
It means that the number of distinct protected libraries that we can implement with this mechanism is small. So in this case, we need one protection key for the library and one for the application. If we had two libraries, we'd need another one for the other library. So basically, we need one for the application and one for every protected library at minimum. And that would give us at most 15 protected libraries for any one application. Well, that's a lot. That's 15 distinct services you could choose to export from the kernel or implement as standalone libraries before you ran out. But it's a lot less than I'd like it to be. Interestingly, VM-Func allows up to 512 contexts. So that's an appealing option if you need more. Its performance was not as good as PKRU, but it still was reasonable. And I would love to see the hardware vendors provide something like VM-Func without hardware virtualization. Because really, it's an independent idea. The idea that I get pre-approved page tables. My application has more than one page table. The kernel set those page tables up for me and believes that I'm allowed to use any of them. Then VM-Func lets me switch between those page tables at very low cost. Unfortunately, right now, it only lets me do that with second level page tables inside a virtual machine, but it would be straightforward, I think, to implement a more general mechanism in some future x86 hardware that would let me switch between pre-approved page tables without hardware virtualization. And that would get around the fact that there were only 4 extra bits available in the page table entry for PKRU and would give us a way to implement protected libraries in larger numbers.
Okay, that sounds cool. And having more than, say, having 16 different databases in a single application sounds enough for everybody, at least for now. And
at least for now. But you know, if we export 3 different file systems out of the kernel that all use the vFile interface but are all implemented in the kernel now, we make them all available as protected libraries, and we make the network stack available as a protected library, and we make a key value store or 2 or 3 available, and maybe a database, and then we take several other kernel services, cryptographic services or something that's implemented in the kernel now, and we try to export that, we might eventually run out. So this is the long-term vision of modularizing the operating system the exact same way that the microkernel people always dreamed, but at higher performance.
Yeah, thank you. And Dmitry asks how protected libraries approach deals with meltdown kind of attacks. So is there a possibility that, say, trick instruction can reveal data from, say, a different protection library?
Yes. Leakage is a concern. Things like meltdown are concerns. And that's on our list of topics to think about. And I don't have any real magic answers for that right now.
Okay, cool. I wonder if the technology can be, or did you contact, say, other vendors for, well, currently the technology is implemented in C, right? So it is a low-level technology. And I wonder if you contacted vendors or platforms for, say, Rust, Java, or other languages to adopt the technology or something around that.
Well, we're not at the point of exporting the code for use by other teams in C and C++ yet. We're close. Other languages, yeah, I'd love to support other languages, Rust in particular for systems programming. I'm also interested in implementing this stuff on other hardware. It should be possible to do it on Power or Z machines. On ARM, the protection keys are available only when running in the kernel. So, ARM doesn't provide user level protection keys. I'm actually not positive whether Power does or not. Z has keys available in both user space and the kernel.
And does it mean that if we use ARM, we have to resort to kernel level APIs? Or is it in the plans
If we
for
want
the
to do protected libraries on ARM, if we want to do protected libraries on ARM today, we have to use something other than PKRU. There's several possibilities. We could do the control software fault isolation, which was mentioned on a previous page. Let's see. Right. We could implement the lowest possible overhead system call to switch page tables. That will be better than a general purpose system call interface. You know, if you we know this from multiple past systems. If there's something like, say, TLB refill that's done in software in your machine, you can work to make the kernel call for that very special purpose. One could consider doing that in order to switch address spaces. It won't be as good as PKU, but it'll be switching address spaces on a stock Linux. I'm honestly not sure whether AMD's hardware virtualization has an analog to VM func. I would have to look. It may. ARM may as well. I'm not sure. But exploring the abilities on other architectures is definitely a cool area for future work.
Okay, and I wonder if we migrate the, say, current application to protected libraries approach, we probably have to replace or rewrite their data layer to be, say, safe from failures. So we cannot take, for instance, if we have an application that deals with the shared memory, just shared memory, I don't know, Postgres server, can we use it as it is, or do we need to rewrite the allocation and the code that deals with shared memories to relloc or something like that?
You have to do a certain amount of rewriting of the library code. So, for instance, in the Memcached case, we had to wrap Hodor wrappers, did the trampoline work around the entry points of the Memcached API. That was what the 600 lines of code that we added were devoted to. But we did not have to change applications. So we tested this with Memslap, your standard HD client, and we linked to it the libmemcached library that one normally links to a client, except that it was our version of libmemcached instead of the standard one. The standard socket IO, ours does Hodor, but the library interface is unchanged, so the application can simply be linked to our Hodor version instead of to the original version without having to change the application code. I think that's important.
Okay, that sounds amazing. So I wonder if we have time left for extra questions, or do we need to wrap up?
That's not my question. I'm happy to talk more, but we're down to the last couple of minutes of our original official time.
Yeah, we have a couple of minutes for the last question probably. So do you have more questions from our attendees, Vladimir?
I think we don't have yet.
Okay. So probably the last question from my side.
Okay.
Dear Michael, probably you attend some conference online. So you know that some of engineering conferences are going online. What about conferences in academia? Do they adopt online approach, or they prefer to move the conferences for the next year, for example?
Well, basically every academic computer science conference that was scheduled between roughly April of this year and April of next year has been moved online. ISCA was online this year, ASPLOS was online, PLDI was online. I was a virtual attendee at PLDI. I have colleagues who attended ISCA and ASPLOS.
Okay.
And, they sort of work. There are lots of problems. What you don't have is bumping into somebody at the coffee table, which I really miss. And of course, you have people trying to attend who are in 24 different time zones.
Oh yeah, time zones is really a problem, because before the talk we had a conversation about what we say, what I have to say to you in the very introduction, like good morning or good evening, because this is probably evening for most of our attendees, because most of our attendees from Russia and from Europe countries,
Yep.
less from the US and other time zones. So it's kind of trade-off. So, and also very interesting thing that
PLDI has an idea. I kind of liked what PLDI did this year. They had everyone record their talk, but then they broadcast the talk. They didn't make it available. They streamed it twice, about 6 hours apart, so that maybe 8 hours apart, so that one of the streamings was likely during waking hours for anybody in the world.
oh
And they required the speaker, just the speaker, to be available for 10 minutes after the streaming for questions in both time slots.
yeah,
Which I thought kind of worked.
Yeah, it's like if you have to choose between time zones of your speaker, of your attendees, let's do the situation uncomfortable for both sides. Probably that's good idea. Okay, thank you very, very much, Vladimir, and thank you very, very much, Michael. And I want to remind to our audience that just below the player, you have a Zoom button, and if you push it and follow the Zoom link, you join the discussion zone with Vladimir and Michael. And Vladimir, a special note for you that probably you have a couple guys from our chat, for example, Andrei Pangin and Dima Tsitelov, and let's make them co-hosts to show the video. I think this would be good for the audience and for them to show the faces to all the people who want to attend. Especially they have questions to Michael. Probably I know that Andrei Pangin, a lot of in the shared memory. I worked in Odoklasniki for the last several years. They have their own library, OneNeo, and this probably he has some questions to Michael. Thank you very, very much.